Hello class, this is CSE 4600, section 62, fall 2024. This is going to be the class introduction and the first half of chapter 1. I'm your instructor, Giovanni Orijuela, and this class was meant to be a in-person section on campus, but that was changed at the last minute to be in an online format. So that decision was not my doing, but I just basically made the whole class async. So, if you need to contact me, email address is firstname.lastname@csusb.edu. If you need to contact me for office hours, and this is how you contact me for office hours, just email me and we can schedule a good time for us to meet and we can talk about it then. So basically, office hours is by appointment. Alright, so this is operating systems. So, a bit of a class overview. So, this is going to be our textbook. It's going to be this big honking book about this thick. And you know you got the right thing when you look at the textbook and you see all the visual puns on it. This is in contrast to this book, which has a dinosaur on the front. You might take 4610 one day and use this textbook instead. So, yeah. One other thing. I thought that it would be the case that we'd go through all the topics in the whole course, but no. Neither book is friendly to that kind of speedrunning. So I would not advise trying to speedrun the whole book in one semester. I don't even anticipate you to memorize, to learn. I wouldn't even expect you to properly learn anything if you tried to speedrun like this. So, what I'm instead going to do is I'm going to more or less cut the book in half, but in such a way that it lines up with the first half of this book. So, what is this book? It's also an operating systems book. It's a lot of the same concepts, but presented in a different way and updated for Windows 10. This one's a bit of an older book, but this is the book that I had when I took operating systems only a few years ago. So, yeah, nearly 10 years ago actually. So, we're gonna be working with this book, but I'm gonna do my best to make it line up with the first half of this book, so that way, when you take 4610 one day, you should be more or less in the middle of this book, because there's a good chance that you'll be using this book instead. So this book is Modern Operating Systems 4th edition by Andrew S. Tannenbaum and Herbert Bose. ISBN 9780-13359-1620. So, I had anticipated that we would go through the whole book, but because these books are so thick, we're probably gonna look through a few chapters, like processes and threads, memory management, maybe deadlocks. But I'd also like to get into security because there's a few important things about security as well. So, I expect the syllabus to be updated for the slower pace of the course because, as I said, would you really want to speedrun this whole book in one semester? Okay, so an overview of the coursework. So, midterm and final are pretty much self-explanatory. They are going to be 25 and 35% of your grade, respectively. The midterm's gonna contain content related to the first half of the course. So anything that we cover between week 1 and week 7, that's going to be midterm material. Everything after that will be finals material. So it's not going to be a cumulative thing either. Midterm covers the first half of the course, final covers the second half of the course. And again, I'm going to have to change the syllabus because I don't want to freak you guys out and say that we're going to cover everything in the book because no. That would probably be way too much content for us to sit down and properly digest. So yeah, expect the syllabus to be updated in the coming days. It is right now, September 2nd, so this is Monday. You're probably just relaxing on your Labor Day, or maybe you're out somewhere doing something else and have yet to return back home. Understandable, as long as you're able to come back here and watch the video in its entirety and learn about the concepts that we're going to look at in the first half of Chapter 1. Okay, so that's midterm and final. We're going to be working with textbook exercises, and I may sprinkle in some labs related to that. So, any textbook exercises that we're going to look at, I'm probably going to sprinkle in a few labs as well. So, I might ask you to do a lab assignment where you basically try out a few system calls and see what happens. There's a operation that I'd like you to try, for example. It's called fork. And it's where one process creates another process that is a perfect clone of itself. But sometimes we want that clone, we want that copy of a process to do something else. So we can, for example, wipe its core memory and replace it with a whole new program, for example. That's something we're actually going to talk about when we get the system calls, by the way. So, yeah, I wouldn't worry about programming assignments in the class, and even then, it probably won't be for at least another week. Anyway, we're going to just look at Chapter 1 for the first 2 weeks of class. So, the first half of the textbook is going to be basically on the base concepts before we get to system calls. And the second half of Chapter 1 is going to be, well, system calls. So, last week I had posted a set of PowerPoint slides covering, well, the introduction to the first half of Chapter 1. Everything up to system calls, basically. And it's a rather abridged, it's a little bit abridged because a lot of the stuff in there is stuff that you would already know. Oh yeah, what is this fourth category of assignments here? Participation quizzes and other assignments. Because the class is async, these are just short answer questions that I may ask you to see whether you're paying attention to the little details regarding the course material. So, for example, if I ask you, if I'm to ask you, can you randomize a mixtape? This would be in the context. This example question, can you randomize a mixtape? This would be in the context of the hierarchy of memory. So, there's a hierarchy of memory where at the top you have the fastest form of memory that a CPU can ever use, but it's so expensive that you can only ever have a very small amount. At the bottom, you would have cheaper, slower, but more capacious memory. And tape drives would fall under that category. So, the one folly of tape drives that makes it not great for storing data on a computer is that if you need to access something at one part of a tape, but you're at a different part of the tape, you have to move the tape until the read-write head is at the right position. So, yeah, it would be, in theory, it would be easy. It would be possible to randomize a mixtape, but how long does it take to move the tape to the right position? That's what I mean by can you randomize a mixtape? And you would answer something like, no, because it would take forever, or yes, but is it worth the time? Is it worth the time? I don't expect there to be one right answer for some of these questions, by the way. So, basically, if you more or less give a reasonable answer to the question, you get full points, and that's going to be your stand-in for participation because the whole class is async. So that's going to be an overview of your assignments. So you have exercises, which will include some programming exercises. You have your midterm and final, and then you have your short answer questions. I mentioned that today is Labor Day, and if so, keep that in mind because a few weeks from now, it's going to be the 23rd, and that is fall census. If you need to drop the class for any reason, the best time to do so is anytime before September 23rd. That way you don't get a letter grade for the class. Anytime after that, you're gonna receive a grade of W. I believe that's how it works, but double check that with how grading works with the entire system. Okay. Academic policies refer to this in the CSUSB built-in for courses for the university's policies on course withdrawal, cheating, and plagiarism. Academic honesty. Basically, don't cheat, don't copy things from other people, and do not ask ChatGPT to write your answers for you. Because according to the CSUSB catalog of programs, plagiarism and cheating may result in penalties up to and including expulsion. You're encouraged to discuss the material related to assignments, but writing down the solutions must be done individually. And exchanging solutions or parts of solutions is not allowed. And when it comes to the attention that is certain that possibly dishonest behavior took place, that's then should report it to the instructor. At the very least, cheating will result on a 0 on that assignment. For adding and dropping a class, refer to this link in the CSUSB catalog bulletin under the adding classes and drops and withdrawals headers. And if you're in need of an accommodation, please contact me, and please also contact SSD at University Hall, room 183, or at the phone number 909-537-5338. It's the student's responsibility to seek academic accommodations for a verified disability in a timely manner. So that's gonna be the whole syllabus, and as I said, expect these topics to be updated in the coming days because, as I said, a big book, don't try to speedrun it. Okay, so that's gonna be the whole syllabus covered. I guess now is a good time to get into the first set of slides for Chapter 1. So this is the first half of Chapter 1. It's gonna be everything up to system calls. So we're not gonna get into that just yet. Rather, we're gonna start things off with a overview of what does an operating system even do. You might be familiar with operating systems in that with the examples of, say, Windows 10, Windows 8, Windows 8.1, Windows 7, iOS, and the different varieties of Linux that might be out there. Linux is a kernel, and I say it's an operating system, but it's just a bare kernel. Yeah, when I say Linux operating system, I just mean anything that has a Linux kernel. Because a kernel is part of the operating system, and Linux by itself, it's just a kernel. You don't have the entire operating system with just the kernel. And for a few examples of Linux-based operating systems, there's Ubuntu, and another one called Mint, and another one called Puppy Linux, which is said to be a very lightweight operating system. Oh yeah, there's Windows 11 now. So yeah, there's Windows 11, and I guess even this book is not outdated, because this one was updated for Windows 10. Okay, so we may be familiar with operating systems and what examples there are out there, but what does it do? What does an operating system do? Why do we need these things? Okay, so as an introduction, a computer is a complex system, and it has all sorts of hardware on it. We have some memory, we have a processor, we have I/O devices such as the monitor, the speakers, the keyboard, the mouse, maybe a printer, maybe a microphone, maybe a web camera. All of this hardware, and so much so that it would be unreasonable to expect a programmer to get anything done if they had to understand every little detail about a computer's operation. I'm speaking into the microphone right now. And how it works is there is a diaphragm that is vibrative whenever sound vibrations hit it, and there's a magnet that picks up these vibrations and turns it into an electric signal that can be parsed as audio. So, do you really expect a programmer to know how to turn those signals back into sound? Probably not. And then you have the reverse for the speakers. So, do you really expect a programmer to write a program that would vibrate the speakers in such a way to produce, like, the music note B flat? Maybe with the speaker that's attached to the motherboard, but not the speakers that are, like, I'm not sure if the web camera can reach it, but I'm actually grabbing my own computer's speakers. Probably not reasonable either to expect a programmer how to do that. And it gets worse. On a hard drive, we have, and this is for hard drives with spinning platters. I don't mean SSDs. SSDs are their own thing. Do you expect a programmer to know how to move the actuator motor that moves the arm in a hard drive to the right spot, and then spin the disk at the right speed, and then have the programmer read the bits on the platter to get information off of it? No, that's unreasonable. The most that a programmer will ever need to do is simply just, well, depending on where you're going, the most you'll ever need to do is know how to call the relevant functions for reading and writing a file, because all that nuance of knowing how to move the read-write head and spinning the platter at the right speed, all that nuance, it's hidden away from us, and that's because in part of having an operating system do all that work for us. So, the parts of a computer system. At the very bottom, we have hardware. And at the very top, we have all the programs that we would like to run on our computer. A web browser. The examples given in the textbook are web browser, email reader, and music player. I would add on to that video games, productivity software, solitaire if it's a very old computer, Discord if it's a very new computer. Can Discord run on Windows XP? Interesting. Don't answer that question right now, so it would be interesting. But it would be interesting if it did. So, at the top you have all the software that is running on your computer, or you would like to run on your computer. And at the bottom we have all the hardware of the computer, the physical things that make up your computer, the CPU, the RAM, the motherboard, the graphics card. So where's the operating system in between all this? That is the very first piece of software right above hardware. So the operating system lies between all our other software and the hardware. The user interface program, that's gonna be something like the text-based interface of an older computer where it was all text. These days we have a graphical user interface where we have a cursor that we can move using a mouse, and then we have windows that we can use to represent an open program. So that's our user interface program. So hardware, OS, UI, and all of our programs. I'll just call it programs. The textbook might call it by something else, application program, for example. I'm just gonna say programs. Most computers have two modes of operation. One of them is called kernel mode, and that is what the operating system runs in. And there's another one called user mode. So kernel mode is the mode that has access to all hardware and can execute any instruction. Operating systems usually run in this mode. After that is user mode, which is where only a small subset of the machine's instructions are available, and most software runs in this mode. Because what good does giving Notepad access to a microphone, for example? So we have kernel mode and user mode. So there are two big reasons why we have operating systems in the first place. One of them, well, maybe I'll get to this. Let me back up. So there are two big reasons as to why we have operating systems in the first place. The first one is to manage all the hardware that makes up the computer. And the second one is to provide a clean and abstract interface for programs to use. So, let me back this up. It's to manage all the hardware and to provide an interface for programs to use. And all of these details we'll get into a little further in the slides. An operating system runs on the base hardware and it provides the base for all other programs to run. There are a few caveats. Some embedded systems may not have a kernel mode at all. Interpreted systems may not have hardware to begin with, because you can emulate a system and basically have an environment where the operating system on that thinks it's running on hardware, but no, we're just mimicking that through software. Some user mode programs may require privileged functions, or it might help the operating system in some way. And the point of all of these caveats is to keep in mind that the borders between these layers can and do get blurred. Because when you have a program that needs to read from a file, that requires something that the operating system can do. So it's going to require calling the operating system, hey, I need to open a file, and the operating system does that operation in the background, basically. Okay, so here we get into the main point of why we have operating systems in the first place. How to provide programmers and programs a clean, abstract set of resources. That's number one. Number two is managing those resources. So, those are the two main reasons why we have operating systems in the first place. So let's explore those. So we think of the operating system as an extended machine, because the architecture of most computers at the machine level language is hard to work with. Do you want to program in assembly language all day? Probably not, unless you're the guy who wrote Roller Coaster Tycoon. Yeah, famous story of a video game called Roller Coaster Tycoon. It was made by a single programmer, and it was like 99% assembly language. That's a bit of an exceptional example, by the way. A lot of the time, we're more likely going to be working with higher level programming languages, such as C, C++, maybe even higher than that. Python, Lua, maybe Java. For example, remember what I said about having the programmer operate the read-write head and spin the platters to read a specific file from the hard drive? We don't do that here, not manually at least. The operating system has a means of providing that for us, so we don't have to go in ourselves, basically. Okay, so a key word here is abstraction. Abstraction hides away the complexity of dealing with hardware so that it's easier to use. So the textbook calls this hiding away the ugly the ugly interfaces and abstracting them into beautiful interfaces that are easy to use. And I have another example here. A piano has like all sorts of little things that... Okay, on one key of a piano you have this hammer mechanism that must fling the hammer up to the string and hit the hammer so it'll vibrate and play a specific note. At the same time, you have this damper that also must move out of the way so that the string can freely vibrate. A pianist should never have to worry about the inner mechanisms of a piano. None of this. Unless you have a really curious pianist. Or you're dealing with a piano tuner. All a pianist really needs to be concerned with is press a note, note plays. And press a note harder, note plays louder. So to play a piano without this would kind of look something like this. And to work with a computer that doesn't have an operating system, this is my visual analogy of what it's like to work with a computer that does not have an operating system. So the reason why we have all the software, the operating system, for example, it makes it easier for programmers to make programs that would run on a computer. Because if you had to do this for programming, this would not be fun. It would not be fun, it would not be easy at all. So the concept of an operating system providing abstractions for programs, that turns out to be a top-down view of the operating system being a resource manager. There is an alternative bottom-up view that says the operating system is there to manage all the parts of a computer. And more specifically, the operating system's job is to provide for an orderly and controlled allocation of these resources to programs that need them. So, at the one end, we're providing abstractions for programs, but on one hand, we are providing abstractions for programs. On the other hand, you can just divvy out these resources willy-nilly. You might have a case where one program is hogging up all the resources. Give me all the resources. And the operating system needs some means of controlling what resources are available and who gets what at any given time. So that way you don't have what are called deadlocks, where one resource is trying to wait for a resource that's being used by another program. So, that's its own chapter, by the way, where we had to do system resource management, so we don't have programs waiting forever for the same resources being available. Here's a simpler example. Imagine you had to print something, but you had 3 different programs you had to print documents from, and you just sent all the information to the printer at the same time. The result would be a mess. So here's what the operating system does. Basically, it makes sure that one program at a time can use the printer, and any of the programs will simply wait their turn. However, it's a little bit more nuanced than that, and it's actually even simpler than that. When a program sends something to the printer, it's gonna go to a buffer, and as far as the program is concerned, it's gonna say to itself, "Hey, I printed the thing. It's not printing." But no, it's in a buffer, and the operating system is basically holding onto this piece of data that's waiting to go to the printer, because maybe the printer's already printing out something already, and once that's done, the operating system's gonna send that data to the printer to print out. Yeah. How much of a mess would it be if you tried to print out like 3 different reports for 3 different classes at the same time, and they all became a mess? So, resource management involves 2 ways of sharing resources, in time and in space. Space-time. A little bit weird that we're talking about time and space now. By time, I mean different programs take turns used on a particular resource. And one of the best examples that you'll ever learn in operating systems is the CPU core. A CPU core can only execute one program at a time, but for nearly all computing systems that we interact with on a day-to-day basis, it's gonna look like the computer's running multiple programs at a time. And it might be. It's just that if you have a one core system, maybe it can't run multiple programs at a time, and it's just switching between programs really fast. And that's how it works, actually. The operating system has to make sure that when programs are being run, no one program is hogging up the CPU core. So basically, it's flip-flopping between different programs, and each program has some time to be run on the CPU. And by space, I mean different programs using parts of one resource. So, as a simple example, you can have multiple programs loaded up in memory, while at the same time, those different programs are taking turns, more or less, on the CPU. So, that's section 1 of chapter 1 already. Chapter 1, section 2 is about the history of operating systems. So, we may, for example, think of computers as inventions that arose in the latter half of the 20th century. But that more or less applies to operating systems. Depending on how you define what a computer is, we may have had computers for hundreds, maybe thousands of years already. And these examples here, this is, I believe that's a schematic or a replica or a part of Charles Babbage's, it's a big calculator made out of gears. And speaking of calculators made out of gears, the ancient Greeks may have beat Charles Babbage by a few thousand years because archaeologists found this little device, this clockwork mechanism at the bottom of the ocean, and it is now known as the Antikythera mechanism. It's a device that calculates the time of when not solar events. It's a calculator. It's a gear-based calculator that would calculate when specific astronomical events would happen. So, depending on what we define to be a computer, we might end up including devices like these. These don't have operating systems. These don't really have operating systems. But we have to start somewhere, so we're just going to skip all of these and go to around the mid-20th century. So, about the World War II era. Yeah, about the World War II era. So, at this time, we would be making computers out of vacuum tubes. Programming languages would be non-existent. And operating systems, what's an operating system? Well, we just talked about what an operating system is right now, but if you ask that to anyone in the 1950s, they'd probably be all like, what? So how would you program on a computer that's made out of vacuum tubes? Well, you would physically hardcode on the program, or you would do it through what's called a switchboard. So if you wanted to run a program, you would have to sign up for a block of time on a sign-up sheet, enter the machine room, and insert your plug board into the computer, and then hope that none of the vacuum tubes burned out in the middle of operation. So this is the first generation of computers. And the thing I said about inserting your plug board into the computer, this would later give way to punch cards. Don't drop them, please. So that's the first generation of computers. Vacuum tubes and the idea of programming as writing stuff that a computer would parse and turn into machine code and then execute, that would not come about for a little while. So that's the first generation of computers. The second generation of computers were reliable enough that they could be manufactured and sold to people, but not like this. Not like this. Not like this. Not yet, at least. these computers would be large mainframes that required it would require trained professionals to operate such big computers, and the only people who would be able to afford these, they would be government agencies, universities, corporations. They're the only ones who would afford such massive computers. And as a bit of perspective, as a bit of a thought experiment. To give you some perspective, we're talking about hard drives as big as a washing machine and can only hold a few tens of megabytes. Meanwhile, I have several hard drives in my computer that can hold several terabytes of information in a much smaller space. And no one was running programs at this time. Rather, they would be running a job. And this is what were called programs, or sets of programs. You would write your program in assembler or Fortran, and later on this would give way to punch cards. You would then hand this to an operator, and then you'd wait for a result. So, the thing about mainframes is they were expensive, so people wanted to look ways to reduce wasted time. So, there might be several jobs in the queue waiting to be run, and people had to find ways to make it so that the operating system was always doing something. I said operating system when I really mean computer, but we're getting into something that modern operating systems would actually do. Keep the CPU busy. So we get into what's called a batch system. Programmers would bring cards to a computer. A programmer would bring a stack of punch cards encoding the program to a computer. And then that computer would read a batch of jobs onto the tape. And then someone would carry that tape onto the actual computer that does the computing. And then, once that's done, the operator carries another tape with the results to another computer that's connected to a printer. And then the printer would print out the results. So that's the second generation of computing. Here's the third generation. So here's the thing about the second generation of computers. They were made from individual transistors. Third generation computers were made using integrated circuits. So all the circuitry of a computer that would now fit in a little square of silicon. And then that square of silicon would be in some sort of... Initially it was a little plastic package that you would insert into a slot. And then that would give way to what we have now, which are like the entire CPUs with all the pins on one side and the heatsink on another side. So this is the third generation of computers. At this time, there were two types of incompatible computers. The first one is computers for scientific calculations and computers for commercial applications. Having two separate product lines was expensive for manufacturers, and some customers, opted for a smaller machine and would later outgrow that machine and would later need a machine that's more powerful than the one they originally got. So the idea of a single family of computers that would be suitable for both use cases, that would start with something called the IBM 360. Its operating system, OS 360, basically had to run on systems big and small and also be efficient on either type of machine. And despite the challenges, it was said to satisfy most of the customers reasonably well. So that's the third generation of computers. And now we're getting into the fourth generation. These are computers that would become so small and so cheap that anyone could buy one. So, remember that Commodore from a few slides ago? Yeah, we would finally be having computers like that. And then it would make way to, like, laptops that were as big as a suitcase. Yeah, as an aside, I would actually like to encourage you to look up what one of the very first laptops looked like. Because it was a big device, as big as a sewing machine. And how it was carried was not unlike a sewing machine in a case. And then, when you opened it, the bottom of the laptop would pop out, and that was your keyboard. You would have slots for floppy drives, and those would be where you would store your files, because hard drives are still too expensive, and floppy drives are just cheaper to use, cheaper to have, cheaper to use. In the very early days of Windows specifically, we would have 2 drives for floppy drives, and they were called A and B. No one really uses floppy drives now, but Windows kept that same naming scheme. So now, even though there are no more floppy drives, for the most part, drive lettering now starts at C. There's a music theory joke that I like to make about this. Why do disk drive letters start at C? And that's because A and B were reserved for floppy drives. If you look at a 61 key keyboard, why does the major scale start at C? And the punchline is because A and B were reserved for floppy drives. So that's the joke. Now, that is 1980 until now. And there's also a bit of a 5th generation, and that was set to begin sometime in the 1990s. Basically, mobile devices. The first handheld phone was affectionately called the Brick, and this made its debut in the 1970s. The first real smartphone would not hit the market until the 1990s, and that was the Nokia N9000. These days, we associate smartphones as being, well, this shape here. And that would not become the de facto shape of smartphones until the iPhone hit the market back in 2007. So the idea is that we would have a device meant for telephony that can also be used for computing. And now we have gaming phones. Okay, so we have a 5th... So here's the problem with this numbering. Some contexts already have something reserved for the 5th generation. And, well, I did end up having to ask ChatGPT for what it thought was the 5th generation of computers. If there is a 5th generation of computers that isn't mobile devices, it's probably going to be something based off of AI or maybe quantum learning or something called neuromorphic computing, designing systems inspired by the brain. If there is a 5th generation of computing, it's probably going to be AI and machine learning or quantum computing, even though quantum computing probably doesn't impact much on the personal computer level. But for now, we're going to stick with this. Right now we're at the 4th, maybe 5th generation as defined by mobile devices rather than AI. If we are already at the next generation, we might be at the very earliest stage. Well, that's all I'm going to say regarding AI. That's all I'm going to say regarding AI, by the way. So, the next couple slides are basically a review of all the hardware that a computer is going to have. So you have the monitor, the keyboard, a printer, a hard disk drive, CPU memory, and then all sorts of controllers for all the other hardware connected to what is called a bus. So this is just review for the parts of a computer. The first thing is the processor. We call this the brain of the CPU because it takes an instruction from memory, decodes what it does, and then executes that operation. And then it does something with the result. And then this cycle, I was always taught this as input, process, output, store. But you may also see the terms fetch, decode, execute. And this cycle repeats for every instruction in a program for the whole duration of a program. CPUs have a specific set of instructions that can carry out, and typically these instructions are not interchangeable between what are called instruction set architectures. accessing, and here's the other thing about processors. If a processor needs to access something from memory, it usually takes longer. Usually takes several clock cycles to get something from memory. So, instead of accessing memory, we'll get into this a little bit. The first thing a CPU is going to do is look into what is called a register. So, a register is a small piece of memory. It's as fast as a CPU, but it can only hold 32, or I guess these days 64 bits worth of data. And those 64 bits are encoding, for example, what registers to read from, what registers to write to, what memory address to load from, what instruction is going to be executed. So that is a bit of a tie-in to computer architecture, by the way. Then we have what's called a program counter. It keeps track of the address of the next instruction to fetch. So, for example, if we are building, say, a Lego truck here, you would be following the instructions, and it might say somewhere in the instructions to repeat steps 20 to 35 like 5 times to make like 5 other pieces that are required for the entire whole of the project. So you may have some jumping around to do in a very complex Lego model. It's kind of no different when a program needs to do a loop. So it might go to some instruction, jump back to the beginning, and do it again several times. The program counter has the job of keeping track of where the next instruction is. There's also something called the stack pointer. So here's the thing about how here's something about how a computer works if you aren't quite familiar with this. And I'm just gonna draw it here. When a computer runs a program, it's going to the memory space for that program is going to have something like this on what's called the stack. It's going to have the main function. And if that main function calls some function, say it's called fun1, that gets added to the stack. And if that function calls another function, let's say it's the square root function, that gets added to the stack. So the stack counter, it basically keeps track of where the program is in its execution, apart from that isn't the program counter. So the program counter is different from the stack pointer. Stack pointer is used to keep track of the current stack. So the stack contains one frame for each procedure that has been entered but not yet exited. So that's what I mean by this illustration of main program at the bottom, and then we added the function 1 on top of the stack, and then square root on top of the stack. It means we called some function 1, and then that function called square root. But we're not done with the square root function until this is popped from the stack. And we're not done with function 1 until that pops from the stack. And what happens when we pop this from the stack? It means the program's done executing. Okay, so yeah. That's program counter and stack pointer. This is a little bit of an abridged version of what the textbook has to say, because some of these might already be familiar to you. But if not, then I would encourage you to read through the book if you have the book already. There is another thing. Remember that process of fetch, decode, execute? In the past, we would do this one after another, but what was done is called pipelining, where you would have different instructions at different stages of this fetch, decode, execute cycle. they would all be run at once at different points of the cycle. And I like to compare this to an automated car wash with separate stations for wash, soap, rinse, dry, wax. Yeah, so you can have many. So the idea is this: you would have multiple cars at different stages of the car wash process. If basically, yeah, you have different cars. You have different cars in the same pipeline, and they would be all at different stages of the car washing process. So one car that just got in is being sprayed down with soap. The car after that is being scrubbed by all those giant scrubbers that flop onto your car and scrub down your car. The car after that might be being rinsed off. Another car after that might be having tire shine applied to it, and then another car after that might be being dried by giant blowers that blow air onto your car and drive your car. And if someone just wants a basic wash, they don't care about the tire shine. When that car enters the tire shine station, they'll just turn off that station so it doesn't shine the tires. And if you want to expand this to another stage, say there is a sprayer for ceramic coating. If someone didn't want to pay extra for that, that station would simply just be deactivated when that car comes in. But if someone wanted to pay for it, then that station would activate for that one car. One of the more prototypical examples for pipelining would be an assembly line, but I feel like a car wash might be an experience that you may have more familiarity with if, for example, you're driving a lot. If you have a car or you drive a lot or whatever, you might be more familiar with the example of a car wash as an example of pipelining than you would be with an assembly line, even though it's the same idea of pipelining either way. Sometimes a program requires a service from the operating system, and this would require what is called a system call, which we're going to cover in section 1.6. That's going to be next video. So that's processors, but everything I said so far, that's just single-core processors. Nowadays, it's a little bit more interesting because we have multi-core CPUs and multi-threaded CPUs. It's called hybrid threading by Intel, by the way. Basically, think about it like this. A CPU can... Basically what multi-threading does is a CPU can hold the state of two threads and switch between the threads as needed. For now, think of threads as separate programs. It's a little bit more nuanced than that, by the way. So, here's the thing. If a CPU core is switching between two different threads, if one thread is stalled because it's waiting for, say, user input, it's going to switch to the other thread in the meantime. And it gets even neater than that. Because now we have stuff like this, hardware like this. The AMD Ryzen 5800X 8-core processor with 16 threads. So it's an 8-core processor, and then each of those cores is being seen as two threads. So they would be reported as two logical processors for each core. So not only do we have multi-threaded CPUs, we also have multi-core CPUs. And the core count for CPUs has skyrocketed in the last few years, at least when it comes to having such high core count CPUs more readily available to consumers. Because now you can get a 8-core 16-thread CPU for about $300 or less if you're looking at earlier generations of AMD Ryzen, for example. So yeah. you may have heard of this yourself, but sometime in 2017, AMD launched the first generation of AMD Ryzen CPUs, and they were basically mirroring the Intel Core lineup identically. So we have Core i3, Core i5, Core i7, and then AMD had the Ryzen 3, Ryzen 5, and Ryzen 7. And then AMD came out with the Ryzen 9, and that was a CPU that maxed out at 16 cores, 32 threads. That costed only about $700. And now we have these high core count CPUs that, depending on how you feel about this, may cost an arm and a leg, but at the very least. Now we have this hardware, and now we have to find some way to use it. So this is where this class would diverge to parallel programming, by the way. And even more so when you consider that there is another piece of hardware that would beat out a CPU, and that's the GPU. I guess that's the only thing that's more powerful than a CPU, at least on most systems. It's a GPU. This is a processor with thousands of cores, and they're all meant for graphical operations, parallel graphics operations. The only thing about them is that they're tricky to program. Typically how it's done is you would write a serial program that would load stuff onto the GPU, and then it would be executed on the GPU, and then it would go back to this EPU. This little thing at the front, that is a GTX 1070. It's an NVIDIA GTX 1070. And right in front of it is this giant skyscraper here. That is an NVIDIA RTX 4080 Super. Let that sink in. Okay, so that's CPU and GPU. Yeah, and I took this picture when I was upgrading my system, by the way. So if you look into a few slides before at this screenshot of Task Manager, that is my actual system. So it is an absolute monster, basically. And if you are also taking any classes with my brother, you might know that his system is even beefier than mine. But I will tell you right now, he does have good reason for that. Maybe you should ask him about it. Okay, now memory. This is the second major component of a computer. There's that memory hierarchy again. So we have registers at the top, and those are those little bits, little things of memory that can hold only 32 or 64 bits worth of data. That is at the very top of the memory hierarchy. And right below that, we have other forms of memory. So, ideally, memory should be fast, extremely fast, abundantly large, and dirt cheap. This is hard to satisfy, so in practice, we instead have multiple tiers of memory. So this forms what we call the memory hierarchy. So at the very top we have registers, and right below that we have cache. So remember what I said about a CPU reading something from memory, and it would take several clock cycles to get that information? Well, cache is there as an intermediary form of memory that is faster than main memory, but still not as fast as a register. And the idea is simple. If a CPU needs to read something from address 1000, it's probably going to need something from address 1001, 1002, 1003, 1004, 1005. So, instead of just reading just that one value, just copy the whole block over to cache, and then read that cached copy instead of just reading from main memory, because that reading from main memory is slower than reading from cache. But reading from cache is not as slow as reading from main memory. And remember, cache is not as fast as the registers, but cache is there to make up for the speed difference with having to read from memory. This way, you waste less time on accessing main memory, since you're just accessing a copy address. You're accessing a copy of what was on main memory, but accessing that copy is faster. You see the concept of caching a lot in other places, not just memory, by the way. So after registers and cache is main memory. This is usually called random access memory or just RAM. And for older computer scientists and older programmers, this may be called core memory. And this comes from how we would make memory from little magnets there. One level below main memory is disks. So we have these magnetic platters and a read-write head that would move on top, over top these spinning platters. These are the characteristic features of a hard drive, or I should say hard disk drive, in contrast to floppy disk drives, which have magnetic disks that are physically floppy. That's why they're called floppy disks. Though the final generation of floppy disks came in a hard plastic casing, the ones that preceded it, the ones that came before, they were always in a floppy envelope. That's why they're called floppy disks. And that's why these are called hard disk drives, or just hard drives. So we have one or maybe multiple platters that are all spinning on a spindle, and then you have one or several read-write heads that move across the spinning surface. And this arm is reading stuff from the disk itself. So each arm position, so there are different places that the arm can go to, those are called tracks. And the tracks for a given arm position form a cylinder. So if you can imagine that these different platters form concentric nested cylinders. Each cylinder is they're concentric cylinders. So this is the typical structure of a hard drive. There is one other kind of drive that you may also know about, and it's called the solid state disk, or more appropriately, or something that might here be called solid state drive. They have no moving parts, so you have none of this happening. Instead, it is a form of memory where it's basically flash memory, where if power is cut off to it when you turn off the computer, unlike main memory, which is said to be volatile, SSDs are a non-volatile form of memory, so nothing gets lost when you turn off an SSD, when you power off an SSD. So that's storage. That's disks and memory and storage. I/O devices are basically everything else that we connect to a computer. When it comes to I/O devices, there are generally two parts: the controller and the device itself. The controller consists of one or more chips and accepts commands from the operating system itself, such as read and write operations. Let's go back to the example of a disk drive. It's gonna have a disk controller, and the controller, for example, the disk controller may be told by the operating system to read sector 11206 from disk 2. The controller then performs the necessary operations. This sounds easy at first, except the controller might also be walking around dead sectors on the disk itself, just to find the data. And then it has the job of transferring all that data to the operating system. So that's one part, that's the controller. The other part is the device itself. These have simple interfaces and they're all standardized. For example, standardizing allows for any SATA disk controller to handle any SATA disk. And because each controller is going to be different, you're going to need different... each controller is different, so you need special software to control each device. And that software is called a device driver. So that's I/O devices. Section 1.3.5 is buses, and I don't mean a bus like this, with the wheels on the bus go round and round, and the funky seat patterns are there to distract you from how dirty the seats are. No, it's a different kind of bus. A bus in computing is a pathway on which data can be transferred on a computer. And the computer is going to have several buses on it, such as PCIe and PCI. These are commonly used to connect graphics cards to the computer. And then you have SATA, which is typically used for SATA drives. And then you have USB. These are typically used for slower I/O devices, such as the keyboard and the mouse. To keep up the pun of public transit, to keep up the fun on public transit, I personally call PCIe PCI Express. Anyway, these slides just basically talk about how the computer boots up. So when the computer boots up, we have something called the basic input-output system that starts up. The BIOS, as it's called, checks how much RAM is installed, and then it checks whether all the other devices are working correctly. And then it scans the buses to see what's attached to them and configures them if they were any different from when the system last booted. And then the BIOS determines the boot devices by trying a list of devices that are stored in what's called CMOS memory. And this is also configurable by the user. Once a boot device is found, the first sector is read. That first sector contains a program that is loaded and executed, and that program reads the operating system and starts that. So, we have a program that loads a program, and then that program loads the operating system. That's an oversimplified view. There's also lots of checks that happens to make sure everything is running just fine. 1.4 is the operating system zoo, so this is just going to be a list of all the different operating systems types there are. So, this is just an abridged version. This is just an abridged version of what's going on here. You don't have to really know too much about these, but I guess it's a good idea to look through these individual sections. So mainframe. So we have operating systems for mainframes, servers, multiprocessor operating systems, personal computing operating systems, which is probably what you're familiar with. Then we have handheld computing operating systems, embedded operating systems, sensor node operating systems, real-time, and smart card. So that's the operating system zoo, and each subsection on that in the textbook is only a few paragraphs long, like 1, 2, only a few paragraphs at most for each one. So I'm not really gonna go too deep into these ones. 1.5 is all the operating system concepts. So we have the process, we have processes, so we have the address spaces, files, input, output, protection, and the shell. And the first one of these we're going to look into it is processes. So you're going to have a program that's going to be somewhere in memory, but it's not doing anything yet until it's loaded. Yeah. So you have a program that's stored somewhere on a hard drive, and it's not going to do anything until it's loaded into memory. Once that happens, it becomes a process, and a process is a computer program in execution. So there's several things that are associated with the process. We have an address space. This is a list of memory locations from 0 to some maximum number, which the process can read and write. And this space contains several things. The executable program itself. It's a stack that includes the program counter and stack pointer. It's going to have a list of open files. It's going to have a list of related processes. And it's going to have other information needed to run the program itself. And your eyes are not deceiving you. I really did take a screenshot of the Windows taskbar and added it to part of the PowerPoint slide. And I did this because you might have multiple programs running on your computer right now. Basically what's happening is each one is its own process. Each one doing different things. Each one having different files open. Each one awaiting user input to do something else. So your computer, what your operating system does, is it decides which process is to be run based on what each process needs and based also on which processes are waiting for something to happen. processes can have their executions be suspended. So basically what also happens is the operating system might decide that a process needs to stop executing even though it's not done. We call it suspension, and that happens when, for example, a process is waiting for user input. And remember what I said about keep the CPU busy? The operating system will simply take out that process, suspend it, so that another process can be run instead. So when a process gets suspended, its state must be saved so we can start again exactly where it had stopped. So in many operating systems, this information about each process, that's called a process table, and this is just an array of data structures, and there's one data structure for each process. So a suspended process consists of its address space, called the core image, and its process table entry. It's entry in the process table. And we need all this information so that when the operating system decides, hey, we can continue with this program again, it'll just start up where it left off. Here's some other things. Processes can create child processes, and then those processes can create their own child processes. This is sometimes done if you have several processes that need to accomplish a task together. But if you want these processes to coordinate with one another, you need something called inter-process communication. Here's a few other things about processes. Each process has a unique ID. Each process also has a unique user ID. That's every process started by the same user will have the same user ID. Every process may also have a group ID. This is for identifying which group a process may be in. So a very simple operating system may only have one program loaded in memory at a time. And running a different program will require removing the previous program from memory and then loading the new program into memory. Of course, that's not what's happening on most computers, so what's instead is happening is basically loading multiple programs into the computer at the same time. This requires protection mechanisms to keep one program's memory from overwriting the memory of another program. And this is done through hardware, but it's controlled by the operating system. So, if we have multiple programs loaded into memory, we want to make sure that they are not overwriting each other. There's another issue regarding memory. How to manage the address space of each process. In a very simple case, the maximum amount of memory in a process's address space will be less than the amount of memory that's on the computer itself, and it will not be allotted any more than that. And if it needed any more than that, even if it used up every byte of memory available on the computer, and it needed more memory than that, too bad, so sad. We don't do that anymore. Instead, we use virtual memory. Parts of a process's address space are basically swapped between memory and the disk as needed. So the operating system provides an abstraction. There's that A word again, abstraction. It provides the abstraction of an address space as the set of addresses a process may reference. So as far as the process is concerned, it has all the memory it can ever access, even if only a small part of that memory is loaded into physical memory at a time. Recall that part of what a computer does, part of what an OS does is provide a clean, abstract model for programmers to work with. And this extends to files. So most personal computer operating systems have the concept of a directory to store its files. So it's basically a tree structure where each entry in a directory is either a file or another directory. So we have a special directory at the very top of the tree I guess it's the bottom because for some reason trees in computing grow downwards rather than up. Starting from the root directory and going down, you can find a path that goes from the root to a specific file. For example, the path that leads to Professor Brown's grant folders would be /faculty/prof.brown/grants. And that's us starting from the root directory. So, root directory, faculty, Prof. Brown. Oh yeah, and then there's the little hiccup of Unix using forward slashes and Windows systems using a backslash for some reason. At every instant, each process has a current working directory. It's basically a subtree. So, in the subtree, you can simply type in /grants, for example. So, in this example, the subtree has Professor Brown be the root of the subtree. So if you have /grants, you're basically going into the subfolder in the Professor Brown folder. Without having to type out the whole path that starts from root directory, faculty, Prof. Brown, grants, you just say /grants. That's it. Okay, so when it comes to files, before you can write or read a file, you gotta open it. But before that, you also need to check whether you have the appropriate permissions. If access is permitted, the system returns a file descriptor to be used in subsequent operations, but if access denied, it gives you back an error code instead. Unix also has something called mounting. Unix has what's called a mounted file structure. If an external drive has its own directory that's separate from the rest of the directory, we gotta find a way. We need a means of combining the two directories into one. So in Windows systems, we would just simply have what's called a C drive, usually, or maybe it's a D drive if you have multiple drives. And if your CD-ROM is, for example, the E drive, it's gonna have E and then the entire directory after that. That doesn't work. It doesn't work the same way in Unix systems, so we have to do what's called a mount. Before mounting, the files on the CD-ROM are not accessible, but after mounting, they basically become part of the same hierarchy as with the rest of the system. So it's basically a means of combining the two directories into one. On Unix systems, by the way. Unix systems also have the following concepts. The special file, which makes I/O devices look like files, which allows them to be read and written to. And there are two types of special files, block special files and character special files. You also have the pipe, which is a pseudo file that connects two processes with one another. So, if you have two processes that are working together to accomplish some task, they need a means of communicating with one another, and one way to do that is to have one process write to a file, and then another process read from that file. And that file is called a pipe. An operating system obviously must also manage things such as keyboards, mice, speakers, monitors, because what good is a computer if it can't take in commands or it can't display results? Every OS has an I/O subsystem for managing its I/O devices. Some are device independent, so it'll work for different types of devices, and some of them are device specific, so they're meant for a specific model of printer, for example. So you might, for example, get a brand new USB mouse and plug it into your computer, and it might not work, and it'll say, the computer might say, I can't use this software, I need the driver for it. Or at least that's how it was in the past. Windows, for example, will have generic drivers, so that if you plug in any USB mouse into it, it'll just use the generic driver, and your mouse is good to go. If sometimes with specialized computer mice such as this thing here, you may need to install a driver to get the fullest functionality out of it. And the same is true with printers, the same is true with other forms of hardware. Protection. A computer typically has things that users want to keep. A computer typically has things that users want to protect and keep confidential, such as keeping malware from stealing your computer's resources, and keeping your banking information, for example, away from prying eyes. So, a simple protection measure, or a simple security measure, would be what Unix calls the RWX bits. So, these bits determine whether a particular user can read, write, or execute a file, and there's 3 bits for the owner of the file, the members of the owner's group, and the system administrator. There's also something called the shell. The operating system is the code that carries out system calls. Other things such as editors, compilers, assemblers, linkers, utility programs, and command interpreters. I would also include something like those system performance monitor programs such as Windows Task Manager under this category. They're not essential for the operation of the computer itself, but they are still important, they're still useful. And this includes what is called the command interpreter in Unix, and we call this the shell. It's not part of the OS itself, but it makes heavy use of the OS's features. It's also a good example of how system calls are used. So you might see in a future lab, we're gonna write a simple shell program to see how the system calls work. I'll give details regarding that as we go, by the way. And 1.6 is all about system calls, but this is gonna be the end of our discussion for today. So 1.6, this is page 50 of the textbook. So basically, if you want an oversimplified look into what system calls are, basically there are system calls for creating processes, killing processes, file management, opening a file, reading a file, deleting a file, and the same thing for directories. And then you also have other miscellaneous system calls. So system calls for process management, system calls for file management, directory management, and miscellaneous system calls. And then there's a small section on the Windows 32, the Win32 API. And then operating system structure, basically the different ways a operating system can be structured. That's 1.7. And then there's virtual machines in there. 1.8 is the world according to C. We might get into that or not, we'll see. And 1.9 is like research on operating systems. Outline for the rest of the book is 1.10, and 1.11 is like metric units, and then 1.12 is the summary of the chapter itself. So we're gonna look into the second half of the chapter in the next video. So as of assignments, nothing is assigned right now, so nothing is due right now. I only give out due dates when there is something assigned. And one thing I've neglected to say regarding assignments is, for most assignments, and this does not include the midterm and final, if you have an assignment being submitted at 11:59 and your internet cuts out, and you submit it at 12:01, I'll still take it. Basically, I give you a 1-week window in which you can submit your assignments on the off chance that, for example, your internet connection cut out. And that's basically my lateness policy. After that, I need a good reason. I need a good reason as to why it's late, and then after that, I may take it after that. But if you have a late assignment that's like 3 weeks late, and there's no excuse as to why it's late, it's most likely I'll just give it a 0. But if you basically submit your work on time, even if it's a few minutes late or even just 1 day late, I'll still take it. Because sometimes the preciseness of the preciseness of UTC can and does cause some weird hiccups to some people in how you must submit something at 11:59, and then you realize your system is like a minute off and it's actually 12:01. It's fine. If it's only late a few minutes, or your internet cut out for half the day and it's like a day late. When it comes to assignments that isn't the midterm and final, if it's up to a week late, I'll still take it. So yeah, that's one thing that is not quite on the syllabus, but I need to mention it right now. There are no due dates because I didn't assign anything yet. But even once there are things assigned, even if it's up to I'll take stuff that is up to 1 week late without penalty. After that, I simply needed a reasonable excuse as to why it's late. Okay? Okay, 1.6 we'll be looking at the system calls, and that's gonna be it for the first set of slides. So, I said this would be available on Monday, but it's like 9 p.m. now, so. And we are already approaching 90 minutes of recording time for this video, so yeah, I think it's a good time to stop the video, let you go, and then we'll follow up with the rest of Chapter 1 after that. Alright? Thank you for watching, and we'll see you in the next video. Take care.